Welcome to ICATS, the International Consortium of Advanced Technologies and Security, and our video and audio and slide series for Thermography Certification Level 1. This is, of course, only a fraction of that curriculum and covers only the basics of thermodynamics. This is video 1 of 3 videos in the Introduction to Thermodynamics. While the entire certification Level 1 thermographers will involve more detailed college-level lectures on physics and thermodynamics, just like certifications issued by the Cal State University system, which this is not, no detailed knowledge of the calculations or formulae will be required. However, some knowledge, a working knowledge of thermodynamics is required, and you will need to be able to discuss the basic principles behind the first and second laws of thermodynamics and think through the issues during your tests. This is an easy presentation. It's just an introduction, and thermodynamics is the study of how thermal energy moves, about temperatures, about heat and work, and of course this series will deal with how that relates to thermal imaging when you're on the job. Thermodynamics lays down the laws of all of science, and while this may sound strange, it is true. All scientific laws are based on thermodynamics, and while we may use the terms first and second law of thermodynamics, often they are simply called the first and second laws, or the first and second laws of science. Men have gazed up at the stars for thousands of years, but the Greek thinkers misdirected us at several key points. The first was thinking that the universe was round or spherical, to them a series of round crystal spheres. The Greco-Roman Ptolemy cued from the Greek thought, and since everything we could see, including shooting stars, fell to the earth, we must be at the center of the earth, and at the bottom, the trash heap, if you will, where things that were imperfect fell to. Nothing in the heavens was considered to be imperfect. It was all perfect and unchanging. Of course, Galileo changed that sometime later. But at that same time, the nation of Israel believed something differently. They thought the universe was relatively flat, described as being like a tent, and that it was being stretched out. Strange, several hundred years later, the Greeks completely disagreed, and they disagreed on a false philosophic pretext on that. 2,700 years later, Hubble, looking at the hailscope in my own backyard up on Mount Palomar, Mount Wilson, proved that it was expanding. And half a century later, in 2003, a little more than half a century, 70 some odd years later, the WMAP isotropic satellite proved it was relatively flat. Go figure. But it wasn't until the hailscope here on Mount Palomar that we started to realize that the infrared spectrum would give us better information about our solar system. Images such as this one where the light is mostly infrared and the colors assigned to different energy levels within that spectrum show us a lot about the universe we could never see before. So, there are two takeaways from this. First, that the thermodynamic laws apply to events trillions of miles away, as well as inside your own body, and even in the smallest of molecules, down to the angstrom level and below. And second, infrared light can be used to image stars, especially supernovae, which have all been discovered since Hubble. In fact, he is the one that first realized that some of the novae, or clouds that were up into the star, were actually not in our galaxy at all. And he's the one looking through the hailscope that discovered that the Andromedan galaxy, for instance, was many times farther than the farthest star away from us, and literally expanded our understanding of the universe. Hubble also was up at Mount Palomar, and the Hubble scope is, of course, named for him. One more issue. Einstein's general and special laws of relativity denied Lorentz's luminiferous ether theory, which claimed that light traveled through some kind of a medium which he called ether, and it was luminiferous ether because that's the medium that light traveled through. What you didn't learn in school, but they're just starting to tell you now, is that Einstein's theory missed 95% of the mass of the universe. That number is actually growing. His friend Lorentz was right. just in case there are those who are shocked by my last statement. While I have been claiming that for better than 20 years, let me first say that you are familiar with the dark matter and dark energy theories, or at least have heard of them. Allow me to quote Robert B. Laughlin, Nobel laureate in physics, endowed chair in physics at Stanford University, from his book, A Different Universe, Reinventing Physics from the Bottom Down. He says, and I quote, "It is ironic that Einstein's most creative work, the general theory of relativity, should boil down to conceptualizing space as a medium, when his original premise was that no such medium existed. The word ether has extremely negative connotations in the theoretical physics world because of its past association with the opposition to relativity. It turns out that such matter exists. Subsequent studies with large particle accelerators have now led us to understand that space is more like a piece of window glass than an ideal Newtonian emptiness. It is filled with stuff that is normally transparent but can be made visible by hitting it sufficiently hard to knock out a part. The modern concept of the vacuum of space, confirmed by everyday experimentation, is a relativistic ether. But we do not call it this because it is taboo." End quote. Well, I tend to be iconoclastic, and what more lofty icon than Albert to classed, but I digress. Here we have an image of the sun, color shifted and cooled until we can see the sunspots really well, and see again when we study even the sun using infrared and thermography of a different kind, we can learn more about the sun. But let's return to the first law of thermodynamics. We'll cover a little bit more of that later, and how Joule explained that and really came to determine that that was true, and what he based that on. But that law states simply, no energy is currently being created or destroyed. If not, then what is happening here? What we see is a lot of energy being redistributed as heat and light to the Earth and to every other place in the physical universe. And this is how thermodynamic laws were developed, not only by studying the sun, but steam engines, when they noted that the more energy you put in, the more you could extract. That's where Joule came along, and where he said the energy had to be preserved in some way or another, but we'll get to that later. Even in the various earth sciences, we find the laws of thermodynamics not only being applied, but even applied to understanding heat and how it works at all levels. The second law states that energy is always becoming less organized, that is, entropy or disorganized energy is always increasing. Like the image of the sun, the heat seen in this Google Earth image is leaving the water and hitting satellites hundreds of miles away from the Earth. To understand why, we need to go to the fourth law that was elucidated, that is the fourth thermodynamic law discovered, if you will, or described at least. But then it was put into first place, and since number one was already taken, they called it the zero law, or the zeroth law of thermodynamics. And that is, energy is always trying to equalize itself, and it will continue to do so until all the energy in that system is equalized as much as it possibly can. I think this is just a corollary to the second law, but apply this to rain. It evaporates from these oceans, say, drops onto the mountains, and then, if not stopped by a lake, runs down until it goes to the ocean again. That's the very process. It flows down the thermodynamic gradient, in this case a gravity-driven pressure gradient, until it gets to its lowest point. Then it's equalized and the zeroth law is satisfied. But doggone, we're back to that pesky Jewish guy they called Isaiah again. How did he know that? He described that system. But there's more to thermodynamics and earth sciences than meets the eye. In fact, that is all we have seen thus far, radiation from bodies near and far. But how else does energy travel?